And here is the example of phase diagram. I have a low boiling point as the throat. For instance, we take a mixture of ethanol and water. So we will have this kind of graph where the x-axis is the composition. Where if we go to the left, if we go to the right, is from left to right is here is 0% ethanol, while here is 100% ethanol, and same goes to when we go to right to the left, it will be 0% water and 100% water because it's a composition. Because the system is composed, or this process is content of two components, which are ethanol and water. And at the y-axis, here is the boiling point of indicate ethanol, while for y-axis at the left indicate the boiling point of water, where the boiling point of water is 100 degrees centigrade, and the boiling point of ethanol is 78.5 centigrade. So how to explain, or what's the information that we can extract from the graph is so the minimums occurs with 95.6% by mass of ethanol in the mixture, where this one. So from the graph, we can state that from the phase diagram, we can state that the boiling point of this mixture is 78.2 here, and then the boiling point of pure ethanol is 78.5 degrees centigrade, while for the boiling point of water is 100 degrees centigrade. So distilling a mixture of ethanol containing less than 95.6% of ethanol by mass will let us collect a distillate containing 95.6% of ethanol in the collecting flask, while what is left is a pure water in the distillation flask. While for distilling a mixture of ethanol containing more, when we talk about more, it should be here, more than 95.6% of ethanol by mass lets us collect a distillate containing 95.6% of ethanol in the collecting flask and pure ethanol in the distillation flask. So for this kind of gun, we can have 100% of ethanol. Whatever we do, we can have the 100% of ethanol. So the best that we can get is 95.6% of ethanol. So if let's see the phase diagram of high boiling point as a truth. So here is the example. Is the mixture of electric acid and water, and again for the x-axis is the composition of electric acid and water. From left to the right is show the composition of electric acid, while from the right to the left is the composition of water. So here's the boiling point. For the y-axis is the boiling point for nitric acid, and for the left is a boiling point of the water. So from here, consider that is 68%. So maximum circle with 68% by mass of nitric acid in the mixture. That is the best that we can have. So the boiling point of the mixture is 120.5 degrees centigrade. While for boiling point of pure nitric acids is 86 degrees centigrade. Boiling point of water is 100 degrees centigrade. So this point, and this point is indicate the maximum of the boiling point of of the mixture. So for distilling a mixture of nucleic acid containing less, when we talk less, it should be this side, less than 68% of nucleic acid by mass. Let us collect pure water in the collection flask, and also isotropic mixture left in the distillation flask. And when we distillate a mixture of nitric acid containing more than 68% of nitric acid by mass, so we will get a pure nitric acid in the collection flask. However, we will have an isotropic mixture left in the distillation flask, and again, we can have 100% of collection by mass of nitric acid for the mixture, because we do have a isotope here, so isotope factor here. So that's why the best, according to the graph, according to the phase diagram, the best that we can have is 68% by mass of nitric acid in the mixture. Okay, let's see. How about the liquid phase diagram, which is a partially miscible liquid? So suppose a small amount of liquid B is added to another liquid A at a given temperature. We can say that is T prime. If it dissolves completely, the main mixture is a single phase. While as more B added, A will become saturated in B, and no more component B will dissolve. So this phase will be vary with temperature, and then we will see the upper critical solution temperature. We can say that we can label it as a TUC. Is the highest temperature at which phase separation will occur, and above the critical temperature, the two components are fully miscible. So this solution is dependent on temperature. As you can see, water and oil phenomena. If we increase at a normal temperature, we can see clearly the separation of oil and liquid. However, when we increase the temperature, we can see that it looks that these two components is a fully miscible. The reason is the greater thermal motion of molecule at a higher temperature will lead to greater miscibility of the components in the system. So for example, we have a hexane and nitrobenzene. We can have oil and water. So for oil and water, I think you can do experiment in your home during this PKP, and you can see clearly the temperature temperature is a big factor, a major factor that can contribute to the miscibility of the component in the solution. As I stated earlier, that the two solubility of the component vary with the temperature. The composition and proportion of the two phase change as the temperature is changed. So we can use a temperature composition diagram to display the composition of the system at each temperature. So here is the temperature composition diagram for hexane and nitrobenzene at 180 m. The upper critical solution temperature, you see here, is the temperature above which no phase separation occur. So below this phase, we can see there is clearly a a two-phase where we can see clearly the nitrobenzene and hexane. And then for the TUC, or the upper critical solution temperature for the system lies at 293 Kelvin and above. Suppose we add a small amount of nitrobenzene to hexane at temperature T prime. The nitrobenzene dissolves completely. However, as more nitrobenzene is added, a stage comes when no more nitrobenzene will dissolve. So this sample will consist of two phases in equilibrium with each other. The more abundant one consisting of hexane saturated with nitrobenzene, the less abundant one, a trace of nitrobenzene saturated with hexane. Besides, we also have a phase diagram of systems that show a lower critical solution temperature, for instance, such as the phase diagram for water and triethylamine. So from this diagram, we see that below this temperature, the two components mix in all proportion, and above, they will form two phases. So the reason is at low temperature, these two components form a weak complex, while at high temperature the complex will break up and they are less miscible. So this is one of example this is the phase diagram for water and triethylamine. Besides, we also have a system where we have upper and lower critical solution temperature, where it have TUC is upper critical temperature and TRC is lower critical temperature. At lower critical temperature, the weak complex disrupts and leads to partial miscibility, while at upper critical temperature, the thermal motion of molecule homogenize the mixture again. For example, this is a graph, this phase diagram for nicotine and water.